You ever look at a huge bridge or a skyscraper and wonder what it's feeling? Under all that weight and wind and pressure? Well, it turns out materials have a kind of secret language. It's how they tell us they're under stress and getting close to their limit. And today, we're going to learn how to speak it.
Right, so everything has a breaking point, from a paperclip to a massive dam. So for anyone who builds, well, anything, the huge question is always, how do we know when we're getting close to that point? How do we stop things from failing catastrophically?
Because it often ends like this. A sudden, really dramatic snap. 1 second, this chain link was doing its job, holding a massive load, and the next, it's completely useless. But here's the thing. That failure wasn't instant. It was sending out warning signs. You just had to know what to look for.
So what is that last warning sign? What's the physical clue that tells us a material is just about to give up? It's not just about how much force you're putting on it, it's about what that force is actually doing to the body of the material itself.
And this is the secret, right here. Before any material breaks, it deforms. It stretches, it squashes, it twists, it changes its shape. Now, this could be a huge, obvious change, like when you stretch a rubber band. Or it could be so microscopic you'd never see it with your naked eye. But trust me, it's always there.
So, to build things that are safe and that last, we can't just eyeball it. We have to be able to precisely measure this change. Engineers call this process of changing shape or size deformation, and measuring it, that's the absolute key to predicting and preventing failure.
So here's the official definition for you. At its core, deformation is really just a change in geometry. Think about the weight of cars pushing down on a bridge deck. That's an applied force causing deformation. But it can also come from something as simple as a really hot day causing a steel beam to expand.
Okay, now this is where things get really interesting. A material doesn't just deform in one nice, simple way. Depending on which way you're looking at it, the orientation, different parts of the very same object can be doing completely different things all at the same time.
All right, check this out. We've got a simple rubber sheet here, and we've just drawn a few lines on it. One going up and down, one side to side, and one at an angle. This is its starting point, its original, comfy, undeformed state. Now, let's pull on it.
And boom, look what happens. The vertical line gets longer, which, makes sense. But, and this is the wild part, the horizontal line actually gets shorter. It contracts. And that angled line, it does both. It stretches and it rotates. This is so crucial to understand. The same exact force on the same piece of rubber creates 3 totally different results, and it all depends on orientation.
And this right here, this is the fundamental shift in engineering. It's not enough to just know how hard you're pushing or pulling. To really understand what's going on inside a material, you have to measure the effect of that force. You have to measure the deformation. And that specific measurement, that is what we call strain.
So strain basically comes in 2 main flavors. The first one is probably what you'd guess. It's all about changes in length. Things getting longer or shorter, stretching and squashing. This is called normal strain.
Normal strain, which we represent with the Greek letter epsilon, is a simple but super powerful ratio. All you do is take how much a thing's length has changed, and you divide it by whatever its original length was. This gives you a really neat, proportional way to measure that stretch or squash.
It's really just a simple before and after story. You start with an object, it has an original length. Then you apply some force, and now it has a new, deformed length. The normal strain is simply that change in length divided by the original length. That's it. So 3 really quick things to remember about normal strain. 1, if it's stretching out, the strain is positive. 2, if it's getting shorter or squashed, the strain is negative. Easy enough? And 3, because you're dividing a length by a length, like inches divided by inches, the units cancel out. So strain is a pure number. It's dimensionless.
But of course, materials don't just stretch and squash. They also twist, they skew, they distort. This change in shape, not just length, is what's captured by our second main type of strain, shear strain.
Shear strain, represented by the Greek letter gamma, is all about the angles. I want you to imagine 2 lines inside a material that start out perfectly perpendicular, okay? Making a nice crisp 90-degree corner. Shear strain measures how much that angle gets distorted when the material deforms.
And this image shows it perfectly. You start with a tiny, perfect square inside your material. Under shear, it doesn't just get bigger or smaller, it gets pushed over, skewed into this diamond-like shape. Those once perfect 90-degree corners are now warped, and that change in the angle, that is the shear strain.
So for shear strain, here are the key takeaways. It's a measure of distortion, a change in shape, not length. We measure the angle in radians, which is just the natural unit for angles in math and physics, and it's caused by forces that act parallel to a surface. Think about scissors slicing through paper or the wind pushing along the side of a tall building.
Okay, so we have normal strain for stretching and squashing, and we have shear strain for twisting and skewing. That's great theory, but how do these two concepts actually work together in the world around us?
Well, let's look at this. It might not look like much, but this is a supercritical component. It's a rubber bearing pad on a bridge, and it sits right between the huge concrete beam and the support pier. This little block is a perfect example of both types of strain in action.
Think about it. The massive weight of the bridge and all the cars on it is constantly trying to squash this pad flat. That's a negative normal strain. But at the very same time, as the sun heats the bridge up and it cools down at night, the whole thing expands and contracts, sliding a tiny bit back and forth. This creates a shearing action, changing the pad's shape, and that's your shear strain.
And that's why this stuff is so important. By understanding and calculating both the normal and the shear strain, engineers can design that one little rubber pad to handle both of those jobs day in and day out for decades, without failing. This principle is literally what lets us build everything safely, from airplanes to our kitchen chairs.
So the next time you cross a bridge or ride an elevator up a tall building, just take a second. Think about that secret language of the materials. They are constantly stretching, squashing, and skewing in tiny, invisible ways, always speaking the language of strain and quietly holding up our entire world.